Welcome to Logarithms Part 2, Applied Electronics. Okay, so here's our question. An amplifier is rated as having a 90 dB gain. What power ratio does this represent? So we know that the dBs or in power is going to be equal to 10 log of power out over power in. We're given the gain of 90 dBs, so we know that 90 dB is equal to 10 log power out over power in. Now we know that we can divide the 10 over, so that gives us 9 dBs equals log power out of power in, and now we can apply our log n equals x and 10 to the x equals n, so that gives us a 10 raised to the 9th power is equal to our power out over power in. And we just want to rewrite that so it's pretty. We've got a power out over power in. That is our power ratio, and it is equal to 1 times 10 to the 9th power. Next question. The manufacturer of a high fidelity 100 watt power amplifier claims that hum and noise in the amplifier is 90 dB below full power output. How much hum and noise power does this represent? Again, we know that our dBs in terms of power is equal to 10 log. Normally we do power out of power in, but it's really our power out is in reference to our power in, so the denominator is the reference. So our noise and hum, right, is what we want to know. We want to know what that is in terms of power. And our power reference is going to be the 100 watts that's at the output. So we want to know what the hum is compared to the output. So the way to set it up is we know that it's 90 dB below, so we know the noise and hum is going to be very small compared to the actual output because it's negative 90 below. So we set that up, negative 90 dB is equal to 10 log of our power, hum, and noise divided by our 100 watts. Again, divide the 10 over, and we've got log n equals x, and 10x to the n, or 10x is equal to the n. So now we can raise the 10 to the negative 9, and that gives us our P, hum, and noise divided by 100 watts. Now we just do the algebra. We can see that our P, power, hum, and noise is equal to 100 times 10 to the negative 9 watts, or 100 nanowatts. All right, next question. An amplifier has an input impedance of 600 ohms and an output impedance of 6,000 ohms, or 6K ohms. The power out is 30 watts when we apply a 1.9 volt signal at the input. A, what is the voltage gain of the amplifier? B, what is the input power and C, what is the power of the amplifier in decibels? Okay, what is AV or delta V, the voltage gain? Voltage gain is equal to V out over Vn. We know we're given what the voltage in when the output is 30 watts, so we'll put 1.9 volts as Vn. Now we need to convert the power out. We know that power out is equal to V squared over R. So if we have a 30 watt and we know what our Z out is of 6K ohms, we can solve for V squared, and then V squared is equal to 30 watts times 6,000 ohms. Take the square root of that. That gives us our V out. And then we can divide that by the 1.9 volts, and that gives us our final answer, a voltage gain of 223.297. Okay, part B of this question, what is the input power? So we know that power is equal to V squared divided by R. We're given a voltage of 1.9 volts. So we can square that and divide that by the input impedance, which is 600 ohms. It gives us a power in of 6.017 milliwatts. All right, part C of this question, what is the power gain in terms of decibels? So we know that we can use 10 log of power out over power in, which is our power gain. So we've got 10 log of 30 watts divided by 6.017 milliwatts. That gives us the power gain, or the gain of this amplifier, as 36.978 dBs. Now be careful, because you might be tempted to use the 20 log V out over V in formula, and that will give you an incorrect answer, because that formula only works when the impedances are matched. In this question, we've got 600 ohms on the input and 6,000 ohms on the output. So we really have to use the power formula to calculate the dBs.